When an apple snaps off a branch, it accelerates toward the ground. We see this downward pull every day. But when we look up at astronauts in orbit, we see them floating, completely weightless. To understand why, we first need to get our vocabulary straight. Gravitation is the universal attractive force existing between any two objects in the universe. Gravity is simply the Earth's specific local pull on the objects around it. Take a look at this formula. This is Newton's law of universal gravitation. F is the total force of attraction. To find it, you take g, the gravitational constant, multiply it by the mass of the first object, then the mass of the second object, and divide it all by the distance between them, squared. If this attraction reaches everywhere and affects every object with mass, it creates a massive contradiction. Those orbiting astronauts shouldn't be floating, they should be plummeting. Resolving that contradiction requires us to look past our everyday experience and dismantle our earthbound intuition about the very nature of a fall. Newton's second law tells us force equals a falling object's mass, m, times g, acceleration due to gravity. Set this equal to the law of universal gravitation. We swap distance for r, representing the Earth's radius. The object's mass, m, appears on both sides, so we eliminate it. This leaves a new formula. Acceleration due to gravity equals the gravitational constant times Earth's mass divided by radius squared. Near Earth, this resolves to exactly 9.8 meters per second squared. This 3D model shows Earth is oblate. Flattened at the poles, the radius line from the center is shorter, making gravity mathematically stronger there. Extend that line to the bulging equator, the radius increases, and the pull of gravity slightly weakens. The math gives us a clean truth. Acceleration is dictated strictly by the planet's mass and your distance from its center. The falling object's own mass is completely irrelevant to its speed. Look at this photograph. If mass truly doesn't matter, why does a heavy person drop rapidly toward the ground while these parachutes drift so slowly? The answer is atmospheric drag. If you drop a heavy coin and a light feather in a standard air-filled tube, the coin easily wins. It cuts through the air, while the feather gets held up by atmospheric resistance. But watch the exact same drop inside a total vacuum chamber. Without drag holding the feather back, they hit the ground simultaneously. This scales to the planetary level. The moon has absolutely no atmosphere. If you deployed a parachute there, it would plummet like a rock. In physics, we call this state free fall, falling solely under the influence of gravity, with absolutely no air resistance or upward forces pushing back. Earth's atmosphere creates a persistent illusion that heavy things fall faster. When you strip the air away, you reveal the universal reality. All objects in free fall accelerate at the exact same rate. This photograph shows the International Space Station. It sits at a relatively close altitude of just 250 miles above the Earth's surface. If we plug that 250-mile distance back into our radius formula, we find that Earth's gravity up there is still operating at about 90% of its surface strength. Gravity is overwhelmingly present in orbit. Zero gravity is an absolute myth. This diagram reveals why they float. There is a downward gravity vector, but also a massive perpendicular arrow. The ISS moves sideways at 17,500 miles per hour. It falls constantly, but this extreme speed carries it over the horizon, perfectly matching Earth's curvature. Those astronauts are not floating because they escaped gravity. Weightlessness is simply the physical sensation of continuous, uninterrupted free fall. From an apple dropping in an orchard to a space station screaming through orbit, there is no difference in the mechanics. The mathematics of universal gravitation bind everything into one continuous, elegant fall.